And our very first lecture on machine learning is on linear methods, okay? So we are going to spend a lot of time on linear methods, right? And you may, at least at the first 1 quarter or so, you may find it a bit boring because this will be probably things that you have seen before in your statistics course, right? How do you actually fit y equals to mx plus c, right? But the reason why I'm going to go very deep into linear methods is that there are very important concepts of machine learning that can be very easily understood using linear methods. And once you understand those concepts, you can transfer those same concepts to other forms of machine learning models, okay? So we also discussed techniques such as regularization and transformation of inputs in the context of linear methods. So again, these are very important concepts in machine learning, and these are probably things that you haven't actually seen in your Statistics 101 course, okay? So a bit of notation. I'm going to use capital letters to denote variables. I'm going to use lowercase letters to denote actual observations, in other words, what's in the data. I'm going to use the dummy index j to denote different variables, okay, so corresponding to different features. I'm going to use the dummy index I to denote different observations, okay, so in other words, things that for example, I do multiple measurements. Each of those measurements will be indexed by I. And I'm going to use bolded variables to represent things like vectors and matrices, okay? All right, let me start with the thing that all of you know and love so well. Everyone has done this in some form, which is linear regression, right? So a linear model is essentially the simplest possible model that you can develop between a target and a feature, right? So all that we are saying in a linear model is that we are going to assume that a linear relationship exists between our feature vectors and our actual target. So a generalized way of writing this is just y equals to b naught, which is your intercept, plus some summation of coefficients bj multiplied by your feature j, okay, xj, right? Now, very frequently when people think about linear models, they may assume it just means the actual measurement of the feature itself. That is not true. Linear models are actually deceptively powerful, okay? Because the features themselves, you can actually just be your raw quantitative inputs, okay? So like for example, let's say I'm going to use the electronegativity as one of my features, okay? It doesn't have to be just the electronegativity, right? I can actually say I can take the square of the electronegativity, I can take the square root of the electronegativity. So these are called transformations of your quantitative inputs, right? And you can also do basis expansions of your inputs. And all these are still considered linear models, okay? You can also add things like interaction between variables. So instead of using electronegativity and atomic number, I can take atomic number multiplied by electronegativity, right? Of course, whether it makes sense or not is a separate question, but I can do it, right, in the context of this model. I can also encode the levels of my input, right? So let's say maybe I'm not particularly concerned about whether the conductivity is 1 times 10 to the power minus 10 or 1.1 times 10 to the power minus 10, but rather I just want to know whether something is I just want to use a category that says metal insulator and semiconductor. I can do that also, okay? So that is what's called encoding of levels of inputs. So in supervised learning, when applied to linear models, basically all that we are trying to do is to say, well, let's say I do multiple measurements, right, of my inputs and outputs. So let's say I'm trying to predict the formation energy from, say, the electronegativity of my elements. I will basically measure the electronegativity of each of the elements, and I measure the formation energy of each of the elements. That would give me a set of paired observations. And what I really want to find here is what are the model parameters, and in the case of linear models, our parameters are essentially the coefficients beta j, okay, that are optimal, right? So we want to find an optimal set of parameters that can map my input to output. And here, when we talk about optimal, we usually define it in terms of the minimization of a loss function, okay? So again, this is a machine learning term, right? When we are training a machine learning model, what we are doing is that we are minimizing a loss function. Now, a loss function just means that it measures inaccuracies, right? So, for example, a very standard loss function you might use is the mean squared error, right? The error between your predictions and your observation. And by summing the square of the errors, that is a loss function, and the smaller the mean square error, you have some way of rigorously saying, well, the model is better if I have a smaller mean square error, right? Now, whether the mean square error is the right loss metric to use, that's a separate question, but you do need a rigorous way of defining how to optimize the model, okay? So let me consider a case of just a very simple example where I basically have just a one-dimensional model. I just have one input variable and I have one kind of target, and the linear model is just y equals to beta naught plus beta 1 x1. Now, in least squares regression, what I say is that, well, the loss function is the sum of the square error given all my n observations. So I'm going to sum all my n observations. I have my observation y of I minus f times x of I, f of x of I. F of x of I essentially gives me the predicted value for my observation I, right? So I take the difference between my actual observation and my predicted observation, and I square that. That's my squared error, and I sum it over all my n observations. That is what is called the sum squared error, okay? Now, and then I substitute in, well, because my f of x of I is just beta naught plus beta 1 x1, so this just gives me this expression over here. And what I want to do is to minimize this loss function as a function of beta naught and beta 1, okay? Now, how do you find the minimum of a function? The way you will find the minimum of your function is you take the first derivative of your function with respect to the variable that you want to find, right? So you will take the derivative of L, the loss function, with respect to beta naught, and you take the first derivative of L with respect to beta 1, and I'm sure you have done this in your statistics course. You can actually get an analytical expression for what your optimal beta naught and beta 1 are, okay? So given all your observations, your beta naught is just given by the average of your y minus beta 1 times your average of your x, and your beta, the optimal value of beta 1 is just given by this covariance between your x of I and y of I, and the variance divided by the variance of x, okay? So this is all very well established in your statistics course, so I'm not going to go too much into details about them, okay? So now we can actually generalize this, okay? So maybe you have only worked with one-dimensional linear regression models before, but we can also generalize this to multiple linear regression models. So here, I'm not going to keep this way of writing it because this is actually a very cumbersome way of writing this expression. Instead, what I'm going to do is that I'm going to write my n observations of y as a column vector, so y1, y2, y3, all the way to yn. I'm going to write my coefficients as a beta vector, and I'm going to write my observations x in this way as this matrix, okay? So, and this linear model is then just represented by this very simple expression, y equals to this matrix x multiplied by my vector beta, okay? So what you can see here is that y is basically a capital N times 1 vector. Beta is a p plus 1 times 1 vector. The +1 comes from the fact that you have an intercept, okay, plus your p variables, okay, and your x is basically n times p+1 matrix, okay. Now, so here your residual sum of squares can also be written as basically a matrix multiplication. So it's just equals to y minus x times beta transpose times y minus x times beta, okay. Now, if you go through the same process as taking the derivative with respect to beta, you can essentially show that your optimal value of beta is just given by this matrix expression over here, okay. X transpose x inverse times x transpose times y, okay, and your predicted y is then of course given by your predicted beta multiplied by x, okay. All right. Now, we can actually visualize this multiple linear regression as a graph. So here I'm showing you a multiple linear regression with basically just two dependent variables, so that we can actually see it as a three-dimensional graph. And essentially, what you see here is this is your predicted values. So this surface actually shows you your predicted values. Your actual observations are the red dots. And essentially, the error in your predictions are the distance between each of the dots and that surface, okay? So what you're trying to optimize is basically you're trying to find that surface that minimizes the sum of the square of the distances to each of those, to the surface, okay? All right. Now, there are some criterion that there are some assumptions that are made when you actually apply a least squares technique, okay? So first of all, one of the key assumptions that people always make is that the observations are independent from each other. So when your observations are actually not completely independent, you actually need to make some adjustments to your model. But by and large, least squares is still fairly robust even if your observations are not completely independent. We also make the assumption that your the variance in your target is a constant, okay? Now, there are ways of adjusting the multiple linear regression model to handle non-constant variance. This is just essentially by weighting your observations by the variances of y itself, okay? And you can actually estimate your variance of your y using this expression over here, okay? So this is essentially the variance of y divided by the number of degrees of freedom, okay? All right, so to make this concrete, I'm going to show you your very first example of how do you build a linear regression model for a materials related problem, right? So the problem that I'm going to show you here is basically the bulk modulus of elements. All these numbers are obtained from the materials project. I'm going to choose a few candidate features that I believe may be used to predict the bulk modulus of the element, right? So things like the melting point of the element, the boiling point of the element, the atomic number, the electronegativity, and the atomic radius, right? So all these are numbers that I can easily get from any tabulated values of the elements of the periodic table, okay? Now, I have a question here, right? Why did I actually choose all these features? Why not something else? Any idea?
What are you trying to predict here?
Bulk modulus. The target is the bulk modulus.
Is there either known or easy to get?
Known or easy to get is definitely one of the useful criteria, but you do need to apply some material science knowledge as to, you have to make some educated guesses, right? What kind of features you're going to use, right? Now, the reason is, of course, things like melting point, boiling point, right? You think about it. If a material has very high bulk modulus, it means that the bonds between the atoms are very strong. they tend to have high melting and boiling points, right? So I do have some sense that this might be correlated with the feature that I'm looking at, right? Similarly, things like atomic radius and electronegativity, again, these have some measurement of the strength of the bonding between atoms. So again, I have some guess, maybe this might be correlated, right? And of course, atomic number I just threw in there just for fun, because for sure, atomic number tells you nothing, okay? Now, you will see actually a lot of material science machine learning papers out there that uses atomic number for some reason, okay? If they do not transform the atomic number, I would ask you to not trust those results, okay? Because the atomic number has no meaning, okay? Atomic number has no meaning in terms of chemistry whatsoever, right? All right. We also add some transformation of these inputs. I'm going to take the square of these numbers and also take the square root of these numbers to generate a longer list of feature vectors, okay? Now, I'm going to demonstrate to you how to go about using pandas for easy data manipulation. So the elemental data that have all these features, things like the melting point, boiling point, atomic number, electronegativity, and radius. It is in this comma separated value file that you see over here, okay? And using pandas, you can basically just read in this CSV file, okay? And to generate things like the square of, say, the electronegativity, I'm just going to create a new column. The new column is called x to the power of 2. And in Python, the operator that gives you the power of 2, the power is basically the double star, okay? So this basically says I'm going to take this column, I'm going to take it to the power of 2, and I assign it to the column x squared, okay? So in your first exercise, in the very last question, I actually asked you to use a pandas data frame and to add in a new column. This is basically how you do it, okay? Similarly, square root x, I just take it to the power of 0.5. R squared and r square root r is the same. And for me to just generate the features, I'm going to create my features by going through all my columns. And as long as the column is not the bulk modulus itself, then those will be my features, okay? And so I'm going to select all my column features and that all my features, and that gives me my input variable, input features x, and my target is of course my bulk modulus, which is this column, which is called k. This is how you go about fitting a linear regression model in scikit-learn, right? And it is important for you to keep in mind this syntax, because you will notice that the syntax, regardless of what kind of model you are using, is going to be almost the same in all cases, okay? So what we do here is that from scikit-learn, we are going to import linear model, which is a whole package of linear models. Under the linear model package, there is a specific class called linear regression. So this is your simple multiple linear regression. And this basically just initializes the model, okay? Now, once you initialize the model, you then go about, you call a method called fit. This basically fits the linear model with your x and y as input, okay? And then you can print out the coefficients and your intercept, right? Now, one thing to note when you actually use this class, when you fit a linear model, is that the x in this case should only contain the features, okay? So if you recall, when we actually generate this vector equation, representation, there is this column of ones over here. This is basically for the intercept, right? So, but when you actually call it in scikit-learn, you do not bother with the 1, okay? So the intercept is automatically added for you by scikit-learn, right? So this is something that you need to be aware of. Now the other thing is that by default, there is a parameter called fit intercept in scikit-learn linear model, linear regression, and that parameter is true. Now, in some instances, for example, you know there's a reason why the intercept must be 0. Then you can set it to false. Okay? So there are instances where that is true. Okay? So, for example, if you are fitting a line between at the absolute temperature and some thermal property, well, at absolute 0, everything goes to 0, right? So then, in that case, your fit intercept should be false. Okay. Now, I do want to go through this link so that you can look at what this documentation looks like. Now, this is the documentation in scikit-learn for the linear regression method. Now, you do need to learn how to read the documentation for scikit-learn, or in fact any kind of Python documentation. Okay, so because when you are actually working with the rest of the models, you do need to figure out what are some of the arguments or keyword arguments that you need to supply to that method. And a lot of times these arguments actually control the model fitting process. Okay, so if you look at this linear regression class, this is one of the simplest class there is, right? So there is only a few parameters that you need to worry about. One is called fit intercept, which is what I just mentioned. Okay, it tells the code whether you want to fit an intercept to your data, right? Now, normalize, you see here it says deprecated. That means you don't need to care about it. It used to be that you can ask scikit-learn to actually normalize the data first. For linear regression models, this is completely useless. For other kinds of models, it's actually very important that you normalize your data before you do any fitting. Okay, so it doesn't apply to linear regression models. Okay, the rest of the stuff are really more controlling the fitting process. So, for example, n jobs basically just means whether I want to spread the fitting through multiple processes. Okay. Typically for linear regression model, you're not going to bother with that. Okay. But in some instances, for example, if you're fitting a large amount of data with a very complex model, you may want to set this parameter to make use of all the processors you have on your very, very powerful laptops that you have today. Okay. So you can read through the documentation to see what kind of what are the users of each of these parameters. Okay, and if you the other section that you need to really look at is basically this section over here, which talks about what are the attributes of this class. Okay, now the attributes are important because after you call fit, the results of the fitting is going to be stored as attributes to your class. Okay, so the most important one for a linear regression model is, of course, coefficient, COEF underscore. Okay, so this tells you basically what are the estimated coefficients for the regression problem. Obviously, if you have not called fit, you are not going to get any coefficients. But here you actually you can actually call for the look for the coefficients. You can also get the intercept. Okay, these are the two features that are two attributes that are the most important, and the rest are really related to the data that you supply. Right? For example, what's the number of features? Did you use 2 features, 3 features, 4 features? Sometimes it's helpful to know what's the rank of the matrix X, and so on and so forth. Okay, but by and large, here the optimized coefficients and intercepts will be stored in these 2 attributes. Okay, now you'll see that they actually talk about other models over here. So C also, this means that these are models that are related to linear regression. Maybe towards the end of today's lecture, we are actually going to get to some of these models. So there's something called the rich regression model and Lasso. These are all linear models, but with regularization. Okay, and the other section that is also very important for you to be aware of is this section called examples. Right? this is always the easiest way to quickly get a sense of how you go about fitting a model, as well as how you get the output out of it, right? Now, so you'll notice that these are basically methods that I already talked about before. So you call a linear regression, you basically fit the model to your x and y. You can score the model. So by default for a regression problem, the score is based on R squared. Then you can look for the coefficients, the intercepts, and you can also predict given a set of input features. Okay? Now, let us go back to our example. Okay, so I'm just letting you run first, okay? But basically, what I wanted to show you is that after you call fit, the score function actually gives you your R squared for the regression, okay? You also can look at the coefficients, and using the coefficients, you can generate the equation that was fitted. Okay, so you see this very, very long equation. This basically tells you that based on the data that I have, the optimized equation for my bulk modulus K is equals to -243, which is my intercept, plus this coefficient multiplied by the melting point, plus this coefficient multiplied by the boiling point, and so and so forth. Now, what you will realize here is, first of all, in this regression problem, in linear regression, the code makes no attempt whatsoever to reduce the number of features. Okay, so you will always get an equation with exactly the same number of features that you put in. Okay, and as scientists, this is something that we may not want, right? We always want the simplest equation that that explains our data, right? So that's what's called Occam's razor, right? So in the end, we will actually need to further improve on this model by using ways of regularization, okay? So right now, the performance of our linear regression model is that we are not doing too badly, okay? We do see that there is somewhat of a relationship between our predicted bulk modulus and our actual bulk modulus. The relationship is reasonably good. The R square is 0.691. Not great, but okay. The mean square error is 3151, okay? And we are going to come back to this example later when we look at other kinds of models, all right? Now, once you do your linear regression, sometimes it is useful for you to understand which of the input parameters are the most relevant to the target that we have we want to predict, right? So under the assumptions of that the errors in your observations actually follow a simple Gaussian distribution, your coefficients beta also will have a Gaussian distribution that is distributed with mean at the predicted value of beta and with the variance given by this expression over here, which is x transpose x inverse times your sigma square, which is where sigma square is your variance of your observations y. Okay? Now, you can carry out hypothesis testing for each of the coefficients. So one of the things you want to see is, well, given that I have this coefficient value, is that coefficient significantly different from 0, right? And the way that you do this is using a t-statistic, and the t-statistic is given by your predicted value of beta j divided by square root sigma square root v, where v is basically the diagonal of your the j diagonal element of your x transpose x inverse. Okay. Now, using this, what you can do is that you can determine whether any of these coefficients are significantly greater than 0, right? So if we go back to this equation, if you look at the equation values, okay, so let me zoom in. So we see all these coefficients. This is 4.25 times 10 to the power minus 2. This is negative 2.48 times 10 to the power minus 1, and so on and so forth. What you want to know is which of these coefficients are actually significantly greater than 0, and whether do they contribute to my prediction of my bulk modulus. Okay, and you can do that with a hypothesis test. More frequently, you don't just want to test one of the coefficients, you can also test groups of coefficients as well, right? So, for instance, sometimes you may have different levels in which you categorize a variable, right? Remember when I said you can actually encode something like electrical conductivity as a metal insulator semiconductor. If those corresponds to k levels, very often you want to know whether that whole set of k variables are actually significant. For that, you actually need to use an F statistic, and here that F statistic is computed using your residual sum of squares with and without your k levels included. Okay, so this is just for background information. Okay, so we are not going to do this too much in this particular class. Okay. All right. Now, we are now going to come to one of the most important concepts in your class. Okay, so if we look at the mean square error for our prediction, okay, we can see that basically the mean square error is equals to expectation of each of my observations theta hat minus the actual predicted value of theta squared, okay? And if we expand this out, we can rewrite this in this way, right? So, and what you see is that the mean square error is basically equals to the sum of the variance of your estimated theta hat plus the expected value of theta hat minus theta itself squared, right? Now, what you see here is basically the mean square errors can be broken down into the variance of the estimate itself and also the square of the difference between the expected value of your estimate versus the actual estimate. So this is what is called the bias, okay? So essentially, your mean square error is equals to the sum of your variance plus the square of your bias, right? Now, in multiple linear regression, there is no bias, right? So the Gauss-Markov theorem basically states that the least squares estimator has the smallest variance among all unbiased estimators, right? So in other words, if you want an estimator for your target that is unbiased, in other words, that this thing is equals to 0, then linear regression, the least squares estimator is the best you can do, right? However, there are estimators that can be biased but provide an overall smaller mean square error, okay? And the reason why such estimators work is, of course, it will reduce the variance of your, it will reduce the overall sum rather than just minimizing the variance itself, okay? All right. Now, we are going to take a quick break from the linear regression model, but rather talk about how do we go about fitting any machine learning model, right? The reason why I'm going through this first is because thus far, the way that I've done my linear regression model is actually an inaccurate way of fitting a machine learning model, right? All I have done is basically I have a set of data, I've thrown all the data into my machine learning model and I call fit, right? Now, that is not a best practice for building a machine learning model, right? When you build a machine learning model, you want some metric of how well that model is going to perform on unseen data, right? So this is where concepts like model performance comes into play, right? So when we talk about the performance of a machine learning model, the performance is always measured relative to independent test data, okay? So just now when I tell you, well, after I finish fitting my model, my R square is 0.692 and my mean square error is 3,151, that is not a measure of my model performance. That is merely the performance of my model on the data that I have already supplied it. I have no idea how well it will perform on data that it has not seen. Okay? So I'm going to limit my discussion here to a very high level, but later when we go back to revisiting the rest of the other models, we will look at how to properly fit a machine learning model such that you have confidence of its performance on unseen data. Okay? Now, there are different ways of measuring model performance. You have already seen one of them, and that's called the mean square error, right? So for the mean square error, the loss function is basically just the sum of the squares of your prediction versus observations, and you take the average of that, right? Now, commonly, another common measure of model performance is called the mean absolute error. Now, the difference here is that instead of taking the square between your observation and your prediction, here you take the absolute value of your observation and prediction, okay? And you then take the average of the sum of the absolute difference between your observation and your prediction, okay? So this is why it's called the mean absolute error, or commonly written as MAE in the literature, right? So when we measure the error, okay, whether it doesn't matter whether we are talking about mean square error or mean absolute error, we do two types of measurements. There is one measurement over an independent test set, and that is called the test error, okay? And there is one measurement over the training set, which is called the training error, okay? So just now what I have reported to you in the example notebook is basically just this thing, training error, right? It is the error, the mean square error that I measure over the exact same training data that I used to fit my model in the first place, okay? Now, as you increase the complexity of your model, the training error always decreases, okay? So this is actually very important, a very important concept, right? So if you think about our multiple linear regression model, let's say instead of having just the melting point, boiling point, electronegativity, atomic radius, and atomic number, I suddenly add another 10 variables to my equation. I say I add the atomic mass or some other, a lot more variables. My training error will always decrease, okay? It will either decrease or stay the same. You will not get an increase in your training error if you add more variables to your linear regression model, okay? However, test errors do not always decrease, right? So this is a very typical relationship between your test and training error as your model complexity increases. Now, model complexity is a very loose concept, right? Typically, it means how many parameters there are in your model. And in the linear regression, in linear regression, it's very easy to intuit what model complexity is. It basically is the number of features that you use to fit your linear regression model, okay? So you'll see that the blue line is my training error. It doesn't matter whether we are talking about MSE or MAE, but you can see that no matter how many variables I add, I always get a decrease in my training error. However, if I look at the red line, which is my test error, which is the evaluation of how well my model performed on an independent test set, you will notice that there is always a minimum point, right? In other words, your test error do not have a monotonically decreasing relationship with your model complexity. When your model is not complex enough, in other words, if let's say I want to predict bulk modulus from just a single variable, which is my atomic number, obviously the atomic number is not going to be sufficient for you to predict your bulk modulus at all. Your test error is going to be very high. Okay? Yes?
If I have, for example, x as a parameter, and I have x squared, is that increasing the complexity or?
Yes, that will be increasing your complexity.
Even if it's the same?
Yes. So when we talk about increasing model complexity, it can either be adding different types of variables or adding different transformations of the variable or using even a more complex equation. Okay? So, so that will actually increase your, if your model is not complex enough, it doesn't have enough features to model your target, your test error will tend to be high. Now, however, when your model is too complex, the same thing can happen. Okay? What happens is that you actually have a model that is fitted to too many variables. It is being overfitted. Okay? It is fitting your training data so well that it is fitting a lot of the noise in your training data. And what happens is that when you apply the model to some independent test data, the error actually is also high. Okay? So what happens here is, of course, that you have this scenario where you have overfitting of the data. Okay? So in other words, not enough features, not enough model complexity, you have underfitting of your data. Too many features, you have overfitting of the data, right? And of course, as you increase your model complexity, your bias actually also decreases, okay? How do you go about rigorously training your and evaluating your machine learning model, right? Now, this is where model selection comes in. So model selection basically is estimating the performance of different models in order to find out which one of the models is the best one. Okay, best according to whatever criteria you choose. Okay, it can be mean absolute error, it can be mean square error, it can also be some other metric, depending on what you care about, right? Now, you then also have model assessment. So that means that after you have already selected what you think is the best model, you also need to report what your final prediction error is likely to be. This gives you some sense of confidence. Well, am I predicting my bulk modulus to plus minus 10 gigapascal or plus minus 100 gigapascal? Okay, so this is basically its generalization error. Now, this is where so in the ideal case, let's say you really have a lot of data. What you will do is that you will take your initial data and you will split the data into 3 sets, right? One is called the training set, which is the data that you actually use to fit the model. You then have a validation set. The validation set is just used to test the performance of different models against your training data, right? And after using the training and validation set, you will basically choose what the best model is, right? And finally, you have your test set, which you would use to calculate your expected generalization error of your final model. Okay? Now, there's no rigorous way of saying what should be the split of your training, validation, and test data. Typically, people use something like 50, 25, 25, which means the majority, 50% of your data is in training data. The other 25% is in the validation set, and another 35% is in the test set. Another common split is 80-10-10. So again, 80% is training data, 10% each for your validation set and test set, right? Now, in some instances, you have very poor data poor situations. In other words, you don't really have that much data to begin with. You may even go down to 95.5, okay? Now, one thing you need to be aware of is that at no point during your fitting process can your test set be seen by your fitting process, okay? So you cannot use your test set to say this is the best model. That is not the use of the test set, okay? Your test set is meant to just be a final model evaluation, okay? The sort of semi-gold standard in fitting a machine learning model is using what is called k-fold cross-validation, okay? Now, it is the simplest and also most widely used approach for model validation. So remember, this is not doing model assessment, okay? Remember, you have already taken out your test set and you put it somewhere, you are not using your test set at all right now, all that you are going to do is that you are going to take whatever data that is in either your validation or your training set, you are going to split it into k buckets, okay? Usually you will do it by random. Of course, there are alternative ways of splitting it. I'm going to come to that later. And you basically have, let's say you use what is called 5-fold cross-validation. In 5-fold cross-validation, you basically split your non-test data into 5 buckets, and you are going to select 4 of them as your training data and 1 of them as your validation data, okay? Now, and what you're going to do is that you're going to repeat this process over k times, okay? So initially, my validation set will be this, and my training data will be this 4. The next round, I'm going to do my validation, choose the second set as my validation data and everything else as my test training data. And then the third round will be this, fourth round will be this, and fifth round will be this. And then I calculate a cross-validation score by taking the average of my validation loss function, okay? So in each case, I will train a model using this training data. I will calculate my error on my validation set, okay? So this is my validation error. I'm going to sum up all my validation error, and for each of the k validation sets, and then I will take the average of that, and that is called my cross-validation score, okay? So this is a trick to essentially generate more random splits of the data such that you actually can have multiple validation scores, and then you have a bigger confidence in your that the model that you chose is actually the best one, okay? Because if you only do a single train validation split, there is a possibility that by some fluke of the randomness, you actually get, you actually erroneously predict one model to be the best compared to another model, right? Here, because you are taking the average of 5 different essentially splits, you have a lower chance of that happening, okay? Now, there are of course many. Again, this is not a hard and fast rule. There's no reason why it should be 5 or 10. It's just a convention that very frequently in the literature people use 5-fold cross-validation or 10-fold cross-validation. There is also something called leave one out cross-validation, which is your k is equals to n. In other words, you leave one data out as your validation set, and you train using the rest of your data, and then you repeat that for each single data point in turn, okay? So that's called LOOCV, okay, in short. In scikit-learn, the good news is that all these things are done for you, okay? So you don't actually have to code up some way of doing cross-validation yourself. Obviously, it's not difficult, but none of us want to go through that process. So in scikit-learn, there is this entire package called model selection. And under model selection, they both have ways of helping you do train test splits as well as doing k-fold cross-validation, okay? Now, you'll notice that typically the way that I structure my cross-validation code is that I define k-fold by itself, because you can actually supply CV equals to 5 to this, okay? But the reason why I do k-fold, I initialize k-fold by itself is because I want shuffle to be true. Because sometimes the data that we actually give you is already arranged in some non-random form, okay? And you want shuffling, you want the code to do some random shuffling before you do any cross-validation, k-fold cross-validation or train test split, okay? All right, let's go take a look at the documentation. Okay, so let me go to this part first. So what you see here is that under the model selection package in scikit-learn, there are many different types of model splitting methods, right? So the one that we use most is basically k-fold. There is something called group k-fold as well. This is when you actually have data where you want to ensure that each of the group is fairly represented, right? So hypothetically, let's say you have a medical data set and you have 1,000 cases with no cancer and only 10 cases with cancer. If you just do simple K4 cross-validation, it may well end up that some of your data sets you have only training data with no cancer, while your test data has all the cancer cases, right? Now, that's not something you want to happen, right? Usually you want some representation in both your training and test data for the cancerous cases. So that in that case, you may do something like K4, group K4 splitting, okay? There's of course that leave one out cross-validation. That's basically the one where the special case where your k is equals to n. And I'm not going to go through the rest. You can check them out later, okay? But by and large, this is the one that we use the most. You can see that to construct K4, the main parameter that you need to give it is the number of splits. So in this case, the default is 5, and it is also the one that we most commonly use. You can also use 10 or whatever number catches the fancy. Shuffle is the other parameter that I use a lot. Note by default it is false, okay? When it is false, that means that it just takes your data as is and then it does the splitting, okay? And this is usually not what you want, surprisingly, okay? Sometimes you already organize your data in some way. You want shuffle to be true to basically split the, to basically randomize the data first, okay? And random state is basically a seed for your random generator. So I would actually recommend that you set it, okay? The reason is because if you do not set the random state, what happens is that if you run your code multiple times, it can lead to non-deterministic results, right? Because the shuffling is random, right? But if you set the random state, basically what it means is that every single time it does the splitting, it will give back the same split, okay? And this ensures that when you rerun your model, you actually get exactly the same result as you run it like 3 days ago, okay? All right. Now, before we actually proceed further, we are going to take a look at some aspects of the data set that we actually was working with just now, right? Which is the bulk modulus with all the elemental features, right? So it is usually a very good practice before you even begin fitting any machine learning model to essentially look at the characteristics of your data, right? So one of the key characteristics that you want to know is there a correlation between some of the feature vectors that you're using? And obviously, in our case, there is, right? I deliberately added in the melting point and the boiling point in my training data set. Now, by definition, melting point and boiling point must have a correlation. That a higher melting point usually means a higher boiling point, right? So it is always useful to do this kind of pair correlation plot. Later, I will show you in code how to do this, okay? And by plotting the pair correlations between your features, you can sometimes decide whether you want to drop some of the features or not, right? So this is where your question about feature selection comes in. If you look at the correlations between your each of the parameters, especially things like, for example, this actually shows you the correlation between your boiling point and melting point, you'll see that it is almost like a linear line, right? So in other words, there's a very strong correlation between your boiling point and melting point. So maybe you will just want to drop, say, the boiling point and just choose the melting point as one of your variables, okay? The rest of the correlations are not that bad. There are some correlations here. These are not really correlations. These are because I already added things like x squared and r squared into my my features. So obviously x squared will have some relationship with x, and r squared will have some relationship with r, right? So so all those things you can ignore. You can also plot it in a heat map like this, and you notice that, for example, again, this basically just shades the squares in accordance to the correlation, and you'll see that boiling point and melting point, they have a very strong correlation with one another. The diagonal doesn't mean anything. Obviously, each parameter will have a 100% correlation with itself, but you will also notice that there are some slight correlations with some other variables, right? Like for example, there is some relationship between your atomic radius and your atomic number. Again, not too surprising, okay? As you go down the periodic table, your atoms get bigger, okay? So this is actually an important step before you actually go about fitting any model, okay? All right, let us go back to our example. Now, so as I mentioned, here I gave you the deceptive impression that our model is actually performing great, right? That seems that once I throw in all the data, I get an R square of 0.691. My mean square error is about 3,151. Now, but what happens when we actually go about using the best practice, right? Which is either cross-validation or we do a train test split, right? So here, I'm going to use just a simple train test split. What is in scikit-learn under model selection, there is a method called train test split, which you just give it your x and y, and you specify how big the test set should be. So this basically says the test size should be 10% of your data. And of course, as I mentioned, I like to set my random state so that I can get reproducible results each time. And basically what happens is that it then split the data into training data, test data for your x, and training data and test data for your y, okay? So, and you'll see that basically this shows you that now my training data set has 74 data points, okay, while my test data has, okay, this doesn't report how many rows there are, but a much smaller set of data, okay? So what you would then do is that, so if you do your you can do your cross validation as well. So that basically uses a train test split. You can actually use the train test split to basically fit the model, but as I mentioned, the best practice is really to do a cross validation. So here we use the model selection. Under the model selection package, there is something called cross validate predict. Okay, I'm going to do 5-fold cross validation. I'm going to shuffle my data, and I'm going to refeed my linear regression model using a cross validation approach. So the benefit of using cross validation predict is that it automatically feeds the multiple linear regression model using my x and y using cross validation, and then it will predict what my y is supposed to be. Okay. So what we then do is that we can calculate the R square by using the R2 score and compare that with what my original observations of y are, and we can calculate things like the mean square error, as well as this is just code to plot the data. Okay, so let's see how well our multiple linear regression model performs when we use proper cross validation. Okay, so this is the result. So this is my predicted bulk modulus versus my actual bulk modulus, and you see that now my R square is only 0.217. Okay, so in other words, previously when I throw in the whole training data into my model, I was basically overfitting the data, right? So it is no surprise that the model will perform well on the training data because the model already has seen the training data, right? So, and the mean square error for when I properly do my cross validation is also a lot higher, and you can see that this plot really doesn't look all that linear anymore, right? There's a significant amount of scatter in my predicted k versus my observed k. Okay? And
So when you do cross-val predict, you use all the data, not just the training or the testing data. You use all of them.
yes, but the way that cross-val predict works is that it do cross-validation. It takes out a test set, it do cross-validation, and then it uses the cross-validated model to predict on the test set. Okay, so and it does that multiple for each data, each split of the data. Okay, so let me go back to so. So you actually will generate a cross-validated prediction for each of the input data points. So in other words, you're using cross-val predict. Each of your input data point is a cross-validated prediction on that data point. It doesn't see that data point. Okay, yeah, but what you should be really doing is to do a cross-validated model and then using the model to predict just the test set. So here we are just simplifying by using using the cross-validation predict to make it into a one-step process.
I see. I didn't see that you do like fitting for the training data. So I'm just wondering.
So no, remember, in cross-validation predict, the code already automatically splits the data into training data and validation data and test data.
I see.
So and then it does a prediction for each of the data sets.
And it stores the model into the MLR.
Yes.
I see.
You will store the best model into the MLR class.
I see. Okay.
So if you look at the returns, okay, what you will return is basically the predictions. You will also let me go back. Yeah, so you will store in the MLR class that you already initialized because it uses that class to do the fitting. Okay. Okay. Now, I'm going to start on going beyond your simple multiple linear regression. Okay, so far we have only worked with our very simple multiple linear regression. And the reason why we go beyond our multiple linear regression model is we want to improve on the least squares model, right? As I mentioned, the least squares model is the best model you can have if you are assuming an unbiased estimator, okay? But to improve prediction accuracy, we can allow for some bias, and hopefully what that biases is significantly reduced variance, and that will also improve our model performance. Now, the second reason why we want to do that is to improve the interpretability of our models, okay? So, as I mentioned, as you increase the number of variables, your model gets, on the training data, it will always improve in performance, right? But you not only do you lose generalizability, you also lose interpretability, right? For example, in physics and chemistry, how many equations do you know that actually has more than, say, 3 variables? Very few, right? Most equations, we like it when our equations have like 3 variables and it predicts the data with 100% accuracy, right? So this is actually a very significant reason why we want to go beyond our least squares model, okay? Now, there are 3 main approaches to basically reducing the number of features as well as improve the generalizability of our model. One is a very simple concept. 2 and 3 are actually much more interesting, okay? So the first method is called subset selection. The second method is called shrinkage methods. What shrinkage method means is just simply that it tries to shrink some of your coefficients down to 0, and then by definition, then those features don't feature in your model at all, okay? Dimensionality reduction just means that given a set of features with n dimensions, can you find a lower dimensional space in your feature space that actually represents most of the variance in your data, okay? All right, let's start with the first one, subset selection. Subset selection is by far the easiest one to understand, but it is also not particularly useful, okay? So subset selection just simply means that I am iteratively going to look at all the different subsets of my features, and I'm going to use that subset of features to fit my model, and I eventually going to find the subset that gives me the best performance, the lowest mean square error on my test set, okay? Now, you can actually, there are multiple ways of doing subset selection. One is called the best subset selection. This is a brute force approach. So let's say I have 5 variables. I'm going to choose each of the 5 variables individually. I'm going to choose pairs of the 5 variables. So 5 choose 2. I'm going to do 5 choose 3, 5 choose 4, and 5 choose 5 variables, okay? And I'm going to fit a model every single time, okay? And I'm going to calculate the test error, and I determine which one has the lowest test error, and that is my best model. Now, obviously, this method is the most rigorous and robust, right? Because by definition, you already found the best possible subset of variables or features that you can use for that model. Now, the problem is, of course, that this method is not very practical once you go beyond just a few features, okay? So let's say if you have 100 features, this is not something you can do within the lifetime of the universe, okay? So, so it is very expensive for large P and large K. So in other words, if you have a lot of parameters to choose from, you can't do it, okay? And also, I just want to note that just because, let's say, the best subset for K parameters includes some particular feature, it doesn't mean that that feature must feature in a subset of a smaller K, okay? So this of a larger K, okay? So this is actually some strange quirk of the best subset model, okay? Now there's heuristical methods of doing subset selection as well, okay? For example, you can do what is called forward and backward stepwise selection. Forward or backward stepwise selection is very simple. So all that I'm going to do is that I'm going to fit, let's say I have 5 variables, I'm going to fit my data to each of the 5 in turn. If it performs best for, let's say, the melting point, I'm going to keep the melting point, and then now I'm going to add either the boiling point, the electronegativity, or the radius, or the atomic number to my data or to my features, and now I'm going to try 2 variables, and then I will choose the best 2 variables, and then I choose the best 3 variables, best 4 variables, and best 5 variables. Okay, so this is basically what is called a forward stepwise subset selection. The backward stepwise selection just means that you do the reverse step. You fit the model to your 5 variables, and then you drop the one that gives you the least reduction in performance. Okay, so one is go forward, start from 1 feature, and then you build up. The other one is you start from all the features, and then you cut down. Okay. All right. Subset is quite obvious, so I'm not going to go through how to do it. It just simply means that you select subsets of your features, and then you go ahead and refit your model and find the best model. I'm going to talk about shrinkage methods. Okay. So the problem with subset methods, of course, is that it is discrete, right? You either retain or discard variables, and that can actually lead to very significant jumps in your model performance. Okay. Now they also tend to exhibit very high variance, right? Shrinkage methods are better in the sense that they are continuous, right? And they do not suffer as much from high variability, right? So the basic concept is very simple. Instead of finding the parameters that minimizes the residual sum of squares, okay, which is our least squares method, we will add a penalty term, okay? And the penalty term basically penalizes more complex models, right? So in the case of linear regression, or most other models, the model complexity is measured by the size of the coefficients, right? It can be roughly measured by the size of the coefficients, right? So the larger the coefficient, the more complex your model is, right? So what we want is that we want a penalty term that penalizes models with larger coefficients, right? And in doing so, when we do the minimization, some of the coefficients will be reduced, and sometimes it reduces all the way to 0, right? And that means that that coefficient, that particular feature is actually not useful at all, right? All right, so let me start with the first kind of penalty term, right? So the first one is called ridge regression. So, and ridge regression is also what is known as L2 regularization of your linear regression model, right? Now, the way that you do ridge regression is that you find the coefficients beta that minimizes this loss function over here. Now, this loss function looks complex, but it is actually very simple, okay? I'm going to break it down for you. So, the first one over here is basically your residual sum of squares, okay? This is basically y, observation y minus my predicted value of my y, right? Beta naught plus beta j xj sum, right? So this is basically the exact same thing as my normal linear regression model, so there's no difference here. The only extra term that you see is this one over here, okay? And this is what is called a penalty term, right? Now, the penalty term in ridge regression is basically just the sum of the square of the coefficients. So you can imagine that if your coefficients are very big, that term then becomes bigger, right? So by minimizing the sum of these two, what happens then is that you not only try to minimize for the square error, you also try to find a model where the coefficients are smaller, okay? So this is how that shrinkage method works, okay? So in other words, it doesn't just blindly optimizes for your residual sum of squares. Now, there is one parameter, unlike linear regression, there is one parameter that you actually need to specify when you're doing a ridge regression, okay? And that is this parameter called lambda, right? So lambda is by definition greater or equals to 0, and it is called a shrinkage parameter, all right? The larger the lambda, the greater weight you are giving your penalty term, right? And that means that the bigger the shrinkage of the coefficients, the bigger the shrinkage that is going to occur on your coefficients, right? So obviously you need to know how to choose lambda, and this is also what is in machine learning called a hyperparameter, right? And what you will do is that you basically test out different values of lambda until you find a model that gives you the smallest test error, okay? And that basically is your optimal value of lambda. All right. Now, one thing to note is that the intercept, if you look at the shrinkage term, okay, j equals to 0 is not part of the penalty term, okay? So the intercept is always excluded from the penalty term, okay? And the second thing when you are doing something with regards to shrinkage methods like ridge regression is that you need to do input scaling, right? So this is something you didn't have to do with simple multiple linear regression, okay? Simple multiple linear regression, whether you scale your inputs before you do the fitting or not, you are going to get exactly the same answer because that answer is analytical. Now, when you are doing shrinkage methods, you do need to scale your inputs, right? And the way that people do scaling is by applying what is called a normal scaler, right? So you will, for each of your features, you will find the average of that features and the standard deviation of your features, and you basically take each of your observations, you subtract the mean, and you divide by the standard deviation of your features, okay? Now, what this means is that you are basically constraining your features such that most of the values are between a value of -1 and 1, okay? And so all your features will now have the same magnitude, right? Why is this important when we are doing a shrinkage method, okay? So if you recall, we are trying to penalize coefficients here, right? what happens when you have a feature that is very small. Okay, so let's say I am measuring my atomic radius, and I'm measuring, let's say I have the atomic radius and I have the ionic radius, and both are inside my feature data set. However, my atomic radius are in units of angstrom, and my ionic radius are in units of nanometers. Now, by definition, the two values are going to be 10x difference, right? And even if the two of them have the same importance, by definition, one of the coefficients is going to be 10x smaller, just simply because of the change of units, right? So that is why we need to do this scaling, all right? This scaling ensures that all your data set will be exactly have the same magnitudes, right? Such that when you actually do the penalization of your betas, the betas are not affected by how you choose the units or what's the range of that feature in question, okay? Another example I can give you, like for example, atomic radius, let's say even if I measure it in nanometers of angstrom, the values are anywhere from 1 to say 5, right? Angstrom, right? Melting point can be something like 1000 K, right? Very different orders of magnitude in features. And in order that this vector does, this coefficient, this penalty term doesn't over bias for very large coefficients, we need to ensure that your data is scaled beforehand, okay? Let me go back to the example notebook, because I want to go through some of the features that you can use in scikit-learn to do both the subset selection as well as the ridge regression, okay? So as I mentioned, subset selection just means that you are selecting the best subset of the k best variables from a set of p variables. So scikit-learn feature selection actually has this thing called select k best, where you can use to which you can use to basically find the best subset of features. Okay, so it's fairly easy. You just initialize the select k best, and let's say I set that k equals to 3. In other words, I'm going to select, instead of 9 features, I want the 3 features that will give me the best performance on my data, right? And you can then basically do this, and you select fit transform, and what that code will tell you is that the best subset of 3 features is basically the melting point, boiling point, and the square of your atomic radius, right? Now, once you actually have that, you can also look at the p-values, but more importantly, what you can do is that then you can go about doing your linear regression fitting again, okay? And here you basically see the results of the linear regression fitting. So this is MLR best is basically the multiple linear regression model based on the best subset, okay? We use cross-validation again, so this is cross-validation predict. Using the MLR best model, I'm selecting, I'm giving it a new x. This x new is basically just the x variables that are selected by my select k best algorithm, okay? And then I calculate the R square MSE, and I do the plot, okay? So all these are just plotting code. I will leave it to you to go through those in detail in your own time. But basically, this is the result, right? So if you look at this plot, the blue dots are basically what we get from our original multiple linear regression, and the orange dot are what we get from our k-best multiple linear regression, right? And what you immediately notice is that using k-best, we have significantly improved the result, right? So our R square is no longer 0.2, it's now closer to 0.6, 0.586, okay? And the mean square error has significantly reduced, okay? All right, so that's the select k-best, okay? So that's subset selection. Now, to do shrinkage methods, as I mentioned, you do need to do what scaling of your input data, right? So the way you do this is from scikit-learn, there is actually a package called pre-processing. And in pre-processing, there is something called a standard scaler. Standard scaler essentially do what I just showed you just now, the equations that I wrote for you. So for each of the columns, they will find the mean of that column, they will find the standard deviation of the column, and they will divide every single value in that column by the mean, subtract the mean from each of those columns and divide that by the standard deviation, okay? So you can print out the means and the actual scaling function, which is the standard deviation, after you get it. But so let me show you. So this is the original set of data. What you notice is that, for example, things like the melting point and boiling point, the values are in the thousands, okay? Things like the atomic radius is 1.95. This is in angstroms, okay? And you can see that these are very different scale, right? So obviously the coefficients will be quite different just from the scaling of the data alone. Now, once I actually do my scaling, so this is actually my scaled data, you will notice that all the values are now roughly between 0 and 1, right? Not 0 and 1, minus 1 and 1, okay? So there are, of course, some values which are slightly outside of that range, but by and large, all the data, most of the data would, assuming that they are following a somewhat Gaussian or normal distribution, most of the 95% of the data points should be between minus 1 and 1, okay? And so now all the columns are now the same magnitude. You can then use that data in your rich regression models, right? Now, I want to show you how this code works because it is actually important. For your lab number 2, you will be doing a lot of model fitting. So in lab number 1, you are not doing any model fitting at all, but in lab number 2, you will be using data and you're going to fit different machine learning models to the data sets that you have, okay? So again, as I mentioned, one of the best practices for building machine learning models and doing model selection is through cross-validation, right? So for rich regression, we do need to figure out what the parameters that you give your rich regression model, what's the best parameter for your rich regression model, right? So remember, in your rich regression model, you have that parameter called lambda, right? Now, in scikit-learn, that parameter is not called lambda, it's called alpha. This is just a name change. There's no difference, right? So what we need to do is to find the best value of lambda or alpha, right? Now, what this code here does is that it basically says I want to look at alpha values from in the log separated space, which is 10 to the power minus 2 to 10 to the power of 2, which is 0.01 to 100. And I want 71 data points between these two ranges, okay? Now here I use tenfold cross-validation. Again, this really doesn't matter. You can choose fivefold. I don't think it makes a difference, right? And what this for loop does is that it goes through each of the alpha in turn. It fits a rich regression model, and then it does a cross-validation to score your rich regression model, right? And here I'm asking it to use the negative mean square error to score the models. What this means is that it's going to calculate the negative mean square error for every single fold of my cross-validation, and then it's going to add put the scores in this variable over here, and I take the negative of that. That is the negative of the test scores. Okay, so remember that it's going to be both training score and test scores, right? So I'm only interested in the test scores. The training scores I'm actually not concerned about, and I'm going to store that in this CV results list. Okay, so for each row in CV results, I'm storing the value of alpha itself, the actual mean square error, the actual average mean square error itself, and the coefficients of the ridge regression. Okay. Now, the next thing to do is just really to plot the results. So this basically plots the mean square error against the values of alpha, and what you can see here is that when your alpha is too small, in other words, your penalty term is not large enough, basically you are doing something similar to just a simple linear regression. Okay, and what happens is that then your mean square error is relatively high, similar to what you actually get with just doing a simple linear regression. And as your alpha value increases, that increases the penalty on the coefficients, and eventually it reaches a minimum at an alpha value of 8.2. And then after that, if you over penalize the ridge regression model, your error then increases. Okay. Now, one thing to note here is that when I do my cross validation for my my model fitting, I use the variable z. Okay, just to clarify, z is basically the data that has already been scaled. Okay, so you have already scaled your data, and this is an important first step before you do any kind of shrinkage methods, right? Now, with the best value of alpha, what we can then do is that we can then go ahead, look at what happens to the coefficients of all my ridge regression when my alpha value changes, right? So again, this is just some plotting code. You can go through it later. This just, oops, I haven't run this. Okay, I need to run the next tree. Okay, this just shows you what happens to the coefficients as your alpha value increases. So what you immediately see is that the magnitude of all your coefficients decreases, right? So that's expected, right? Because as the penalty term increases, the bigger the penalty on your sum of your coefficients, and the more shrinkage you get. All right. Now, you should also notice that none of the coefficients really reach zero. It goes towards zero, but they don't really reach zero directly. Okay, so this is a feature of ridge regression, right? Now, you can also get the intercepts and the coefficients, and you can print out what is the equation of your that is being predicted by your ridge regression model. Okay. So it is just a linear model, right? There's no difference between this and your normal linear regression, except that you have introduced a penalty term and now some of the coefficients are smaller. Okay. We can compare that to our standard linear regression. So this, again, this just uses the best value of alpha that we have found, and we look at, we plot the results of the ridge regression, which is the orange dots, versus our normal simple multiple linear regression, which is the blue dots. And again, you see a significantly improved performance. Now we get R square of 0.60, and the mean square error is 4,000 or so, about. So it has reduced by almost half. Okay, through the use of our ridge regression. Okay. All right. Any questions here before I proceed to the next shrinkage method? All right, if not, let me go back to the slides. Okay, now the second type of shrinkage methods that is commonly used is what is called Lasso, right? Lasso stands for least absolute shrinkage and selection operator, so LASSO. Again, this is very commonly used, and personally, this is actually my favorite form of regularization compared to other kinds of regularization. It is called L1 regularization, right? And in L1 regularization, the only thing that is different is your penalty term, which is right over here, right? So recall that in your ridge regression, the penalty term is basically the square of the sum of the squares of your coefficients beta. So here, instead of the sum of the squares of your coefficients beta, you take the absolute values of beta, right? Otherwise, it is in principle largely similar, right? It reduces the coefficients, and again, you have a parameter called lambda that you actually have to specify that determines how much shrinkage you want, and you obviously have to find an optimal value of alpha. Lambda, right? And in the code is called alpha. So again, just like the ridge regression, the intercept term is also not part of the penalty, and also your inputs needs to be scaled before performing lasso, right? And this is exactly the same as in ridge regression for exactly the same reasons. So let me go to the code example. So the code example for ridge regression is very similar to the one for lasso. Again, I want to find the optimal value of alpha, and the only difference between ridge and lasso is just this, right? That you change this from ridge to lasso, and that's all, right? The rest of the code is almost exactly the same. So like before, we are trying to find the optimal value of alpha. We generate, we do cross validation, and then we let the code run, and we find that the best value of alpha is 3.36 in this case, okay? And we can then plot again the coefficients with respect to the value of alpha, right? Now, this is where things become very interesting. It is very different between ridge regression and lasso. You'll find that unlike ridge regression, where you actually have a very smooth curve of decreasing coefficients with alpha, what you see here is that the behavior is a lot more non-smooth, right? And in some instances, beyond certain values of alpha, what you find is that certain of your coefficients get shrunk all the way to 0, right? In other words, lasso is not just a shrinkage tool, but also a feature selection tool. So if you have a coefficient that is shrunk to 0, that just means that that particular feature is not important for predicting the target that you have in mind, okay? So you see that, let's say, if I take this, which is my electronegativity, we see that just beyond a value of about 0.1 in my alpha value, I basically get the coefficient for the electronegativity is basically 0, okay? And as you increase your value of alpha, some other coefficients also goes to 0, right? So obviously you can go too far, and eventually you basically end up with just one variable, okay? But that's basically how it works, okay? So using the optimal value of alpha for our lasso in this case, we actually can again print out the equation, and this is basically the equation for my bulk modulus from the features that I originally provided it using the optimal value of my lasso regression. And again, here is again where you see a lot of difference between the ridge regression result and the lasso regression result. So if you go back to the ridge regression result, you see that essentially the equation is as long as your linear regression model, right? That none of the coefficients have shrunk to 0. They can shrink to some small value, but none of them are shrunk to 0, right? So you still have however many variables that you started out with. In lasso regression, because some of the coefficients have shrunk to 0, you only have 3 non-zero coefficients, which is your melting point, boiling point, and square root of x, okay, which is your electronegativity. So this just means that the optimal model actually only comprises of 3 features and not 9 or something that you started with, okay? And you also notice that some of these features are similar to what you actually get from your best subset regression. So that is reassuring, right? So that regardless of which method you use for feature selection, you still get the same features, okay? I'm going to check the chat later and look at the question, but here basically shows you the results from your Lasso regression versus the multiple linear regression. Again, the performance obviously has improved. R-square is higher, MSE is also much lower. They are not much better than the ridge regression, but the model is also a lot simpler, right? So now you don't have 9 variables, but rather just 3 variables that predict your bulk modulus, and the performance just as good. And as scientists, we like that, right? We like it when a simpler model would already have a high predictive value compared to a much more complex model, okay? All right, so so we can actually visualize the difference between subset versus ridge versus Lasso using some artificial data. So let's say we consider a set of orthonormal features. Orthonormal just means that the features have no correlation with one another whatsoever, okay? So we can compare, let's say, what happens when we have ridge regression, subset regression, and Lasso regression. And in ridge regression, essentially what you have is a proportional shrinkage. What that simply means is just that each of the coefficients are shrunk by the same amount, right? And same proportion, right? And none of the coefficients are actually set to 0, okay? So this shows you essentially what happens to the coefficients as you change your value of your parameter, right? In Lasso, what you actually have is what is called soft thresholding, right? You actually translate your features coefficients by a certain factor, okay? And if that factor happens to let the magnitude go below 0 in terms of magnitude, it then gets truncated, right? So this is why Lasso is actually useful in feature selection, because some of the features, when you actually do this shift, it basically says that this feature is not as important, and at a certain value of the penalty term, this coefficients then become 0, and that feature no longer is features within your equation, okay? The best subset is, of course, what is called hard thresholding. In other words, you are essentially just saying, I'm only going to select 3 coefficients, and if there are whatever 6 or 7 other coefficients that do not perform better than the 3 coefficients, I'm going to throw them away, okay? So that is why it's called the best hard thresholding, okay? So that's the difference between the 3 different value methods of shrinkage and subset and feature selection, okay? Okay, there are other shrinkage methods. I am not going to go through them simply because by and large they work on the same principle. So you should be just aware of ridge and Lasso at a minimum, and eventually if you want to explore the other shrinkage methods, you can go ahead and read up about them, and when you do so, the principles are again all the same, okay? So they are not that different. Now, the one that is an obvious extension of the ridge and Lasso is just simply called the elastic net penalty. This basically just takes the sum of your ridge regression penalty and your Lasso regression penalty, and you take some linear combination of that and use that as the penalty term, okay? Now, this obviously have an additional term called alpha that you have to figure out what's the weight between your Lasso and ridge regression term that you that you need to optimize for, okay? And there's also something called the least angle regression. Again, very, very similar in principle. So you can, if you want to explore those methods, by all means look up the scikit-learn literature as well as other data science textbooks, they may go through those. Okay. All right. Now, remember, so there are 3 different ways of doing feature selection, and the last one is called derived input direction. So a derived input direction just simply means that I'm going to do a transformation of my input variable feature set into a smaller subset, so that dimensionality of my transform variable should be smaller or equals, okay, to my original dimension of my feature set. And then instead of regressing on my full feature set, I'm going to just regress on the transform subset. Okay. Now, the most common way of doing this is what is called principal component analysis, and you do principal component analysis on your feature set to transform non-orthonormal features into orthonormal directions. And okay, so this is called PCA. And then instead of doing regression on X, you do your regression on the first M directions that have the highest eigenvalues, right? So in PCA analysis, what happens is that you find the directions that explain most of the variance in the first direction, and then you have the second highest variance in your second direction and third highest variance in your third direction, and so on and so forth. Okay, so what you would then do is that you basically choose the highest variance one. That just means that it describes the variability between your data the most. Okay, and then you then use those to do your regression. Okay, we are going to revisit PCA in a later lecture, so I'm not going to go through that here. What I'm going to go through is what is called partial least squares. So partial least squares essentially is a algorithm in which you try to find directions in your data that have not just high variance but also high correlation with the target variable. Okay, so the algorithm is actually fairly simple. So you compute your first the inner product of each of your feature vectors with your target, okay, for each of the feature vectors. Okay, for the first transform direction, what you do is that you basically take the sum of those coefficients that you just calculated with your feature vectors, and this is basically just equals to the sum, the weighted sum of each of your feature directions by the strength of its effect on y. So in other words, the stronger the effect of your feature vector on the actual target y, the greater weight it will be given. Okay, so so basically you get this first transform direction, and then you will then regress your y on the z1 to obtain your first data. Okay, that gives you your first coefficient, and what you would then do is that you orthogonalize your vectors, your feature vectors with respect to z1 using this formula over here. So basically this just creates new feature vectors that are orthogonal to the first transform direction, and then you keep repeating this until you have p coefficients, and p is of course some number that you can choose, right? Whether it is two directions, which is very common, or you want to do 3, 4, 5, or whatever number that is required to basically give a good performance on your model. Okay, so this is what is called partial least squares, right? Okay, so let me go back to the code examples. So we already went through Lasso. So in partial least squares, partial least squares regression is under the cross decomposition package of scikit-learn. So again, this is very, very simple, right? In scikit-learn, you just basically take the PLS regression, you tell it the number of components that you want. So in this case, I say I want 2 components. So the reason why people like to choose 2 as a number of components is that you typically can plot that quite easily. You can just plot the predictions versus component 1 and predictions versus component 2 in a XY plot, and that's very easy to visualize, right? Now, obviously, there's no rule saying that you just need to keep it to 2, okay? So typically, people choose 2 just for ease of visualization, okay? And this basically just plots the result of my partial least squares, and what you see is that again the R square is significantly improved with this partial least squares directions. So in other words, by transforming our input data, we actually get a much better prediction performance, both in terms of the R square as well as the mean square error. Okay. Now we are going to move on to modifications of our linear model that can significantly increase the power of what we think of as a very simple model, right? So it is very highly unlikely that the true function that you are after, so let's say you're trying to predict something from a function of x, it is very unlikely that the true function is actually just linear in x, okay? There are situations where linearity is a reasonable assumption. So for example, if you have very small displacements about a point, you can use your first order Taylor series expansion, and we know that about the equilibrium point, f of x is just equals to f of a plus your derivative of f of a times x minus a plus the second derivative of f of a times x minus a squared over 2 factorial, and so on and so forth, right? So this is basically my Taylor series. Now, if the displacement is small enough, you can always ignore your higher order terms, and then essentially what you get is a roughly linear model, right? And this is of course something that is very frequent approximation that we use quite frequently in physics, in chemistry, and in material science, right? So if you think about your Hooke's law, right? Hooke's law just says that the force on the spring is equals to some constant k times the displacement of the spring, right? And that linear elasticity regime is basically comes from this Taylor series expansion, okay? So there are situations where just a very simple linear model would actually be sufficient, right? But more often than not, what you want to do is to enable us to model much more complex functions using a basis expansion, okay? Now, the general concept is fairly simple, right? So instead of just having x1, x2, x3, x4 as your feature vectors, you instead use a function of your x1, x2, x3, x4, and so on and so forth, okay? So what you are doing essentially is that you are expressing your f of x as some linear function of your linear function of functional transformations of x, okay? This is also why it's called a linear basis expansion in x, and obviously how well your model performs then depends on the choice of your basis functions, right? So the h of m, how do you choose h of m, right? So hypothetically, let's say I want to create a polynomial model, right? Then h of m is just simply equals to x to the power of m, right? So that will give me beta 1 x plus beta 2 x squared plus beta 3 x cubed plus beta 4 x to the power 4, and so on and so forth, okay? So that's one way of transforming x. Now, we don't actually have to use polynomials, but that is basically one potential function, right? So that's the first one that we see here. So these are some examples of different basis expansions that you can use for your h of m. So one is basically just polynomial. You can also do the logarithm, the square root, the exponential. These are non-linear transformations in x. Now, surprisingly, this should not come as a surprise to you, but these functions are actually very frequently used, right? Because if you think about, for example, your Arrhenius relationship between something like the conductivity of a material versus the activation barrier, or the reaction rate versus your activation barrier of your reaction, it actually follows some exponential form, right? So you can then use exponentials of your variables as a basis expansion. These are some other not so obvious ways of creating basis expansions, okay? One is something that I suspect a lot of you have done before, but you may not be aware that you are actually doing it, right? And that's basically saying you split the function into different regions, and then you do piecewise fitting to each of those regions using some polynomial, right? And this is where your the concept of the cubic spline come about, right? So you probably have done cubic splines before in your career, right? So very often we have a set of data and we just use the Excel function, please fit a cubic spline, and then we don't really understand what's going on behind that cubic spline. Here we are going to learn how you actually go about doing a cubic spline, right? At least the theory behind doing it, right? And the most powerful one is, of course, you would actually choose basis functions that are orthogonal and complete, right? Complete just simply means that with that set of basis function, you can potentially represent any function, and you can do it very efficiently, right? So some examples of basis functions that you have seen before in the literature are things like Gaussian basis functions. So if you are working like me on solving the Schrödinger equation, you know that things like Gaussian basis functions are very often used. Things like plane waves are also very often used as basis functions for doing your fitting, right? So sometimes you use basis functions not really to because you actually think that there is a polynomial relationship between the terms, or you may not even think that there's a Gaussian relationship between the input variable and the target, but rather you use the basis function essentially just as a way of creating a more flexible representation of your data. And with that more flexible representation, you can actually significantly improve the performance of your machine learning models, okay? Now, if the basis functions are very complete, they can be very large, and some basis functions are essentially infinite, right? Like, for example, Gaussian basis functions, you basically have a infinite number of Gaussian functions that you can use. Then what you basically have to do is to either restrict the basis function using some criteria. Let's say you just, for example, let's say polynomial powers, you're going to go up to maybe x to the power 4 and no further. You're not going to go to x to the power 5. More frequently, you go to just x squared, okay? You also need to do some form of selection and regularization, right? So this is really where your Lasso and rich regression comes into play, and you can then use them to select out which of those basis functions actually contribute to your fit and which ones don't, okay? Okay, so this is just to show you some examples of situations where we actually have basis functions. So for example, your Arrhenius relationship, reaction rate equals to some constant times the exponent of negative EA over RT. EA is basically just your activation energy. To linearize this equation, you would take the log of the equations on both sides, and basically here you have 1 over t as one of the features, and your target is basically R, okay? The other one is the Ising model. Sorry, your target is log of R, right? And the other one is the Ising model that is very frequently used to model lattices, especially things like magnetism in lattices, or configuration or order in lattices, okay? And this is basically the form of the Ising model, where you basically have the product of your spin terms, okay, what they call the spin terms between neighbors, and this thing called the exchange parameter, okay. So for example, sigma I is 1 if it is a up spin, and it is -1 if it is a bottom down spin, okay. So something like these two pair will give you a 1 times -1, so it's a -1 over here. Jij can be either positive or negative or close to 0. If you have a positive number, essentially what this says is that you prefer light spins to be near light spins, and that will give you some form of ferromagnetic configuration, while if it is negative, you tend to get an anti-ferromagnetic configuration, okay. Again, so here, of course, the basis functions is basically that cross multiplication of these two terms, right? So just to show you that this kind of approach has been used substantially in the literature. So this is one of the examples in cluster expansions, where essentially you are doing a Ising-like model, okay, and you have your j term, your j of term, and your product of your spin terms. So it can be 2 spins, 3 spins, or what we call clusters, okay. And in recently, people have been using things like compressive sensing, which is essentially just a lasso to basically figure out which of these j terms would be which of these j terms are 0 and which do not contribute at all to the energy of the system, okay. All right. Now, for the last 12 minutes or so, I'm going to talk about something that you are very familiar with, which is your cubic splines. So as I mentioned, another type of basis functions is that basically you split up the functions into different regions, right? So for example, I will specify that in h of one of the basis function is h of 1x, applies only when x is smaller or equals to some value eta. The other basis function h of 2x is applies within the region of x between epsilon 1 and epsilon 2. And finally, I have a third region which only applies when x is larger than epsilon 2. And then you have to decide what should be the value in each of these regions, right? Now, there are a few ways in which you can do this. One is called, the simplest way is to do a piecewise constant, right? All this means is that if x happens to be less than epsilon 1, I'm going to just take the, I'm going to give it a constant value. And this is basically what results, right? So obviously the best constant value predictor for this region will just be the average of that region, right? So then the green lines basically give me my prediction for such a fitting, right? So the parameters when you do this kind of piecewise polynomial is, first of all, you have to decide the number of knots, right? Number of knots just means that am I choosing just epsilon 1 and epsilon 2, or am I going to do epsilon 1, 2, 3, 4, 5, which is 5 knots, or am I going to do more than that, right? I also have to decide the order of the polynomial to fit the data in each of these regions, right? Now, piecewise constant just means that the order of the polynomial is 0, right? Now, I can of course choose a linear model for each of these regions, in which case I do a linear regression in region 1, I do a linear regression in region 2, and I do a linear regression in region 3, and that basically gives me my piecewise linear model, right? Now, there's also the third parameter that you have to choose, which is what's the continuity at the knots, right? Do I want to ensure that my knots are continuous based on the first value? Do I want it to be continuous even in the first derivative, or do I want to be continuous in the second derivative, and so on and so forth, right? Typically, that relates to the second parameter, which is the order of your polynomial. So if you have a polynomial of order n, we usually want all the derivatives less than n to be continuous, okay? So this is basically what happens when you do a continuous piecewise linear fitting to this data, which is you basically have a continuous value you have linear functions in each region, and the values at the edge at the transition points epsilon 1 and epsilon 2, they must be continuous, right? You cannot have a jump in your values like this. Okay, all right. So cubic splines, in terms of this type of piecewise polynomials, the most common one that everyone is familiar with are called cubic splines, right? So cubic splines just means that I'm going to use a third degree polynomial for each of my regions, right? So I'm going to create for each of the regions, I'm going to take the data, I'm going to fit the best third degree polynomial to the data, all right? Now, typically I don't just want just that, because if let's say I just fit a third degree polynomial to this region and then fit another third degree polynomial to this region and another third degree polynomial to this region, what I would get is something like this, right? And you will see that there's gaps in the predictions at the edges of my of my pieces, right? So because this is a third degree polynomial, I typically want both my first and second derivatives to be continuous, okay? So in other words, I don't want there to be sharp jumps in the values. I don't want there to be sharp kinks in my first derivative. I also do not want kinks in my second derivative. So you see that if you have continuous but you still have a discontinuous first derivative, this is what happens, right? The values do not jump, but you actually have a sharp change in your gradient at the edges, right? So if you have a continuous first derivative, things become a lot smoother. And finally, if you actually have a continuous second derivative, this looks perfectly smooth, right? So the way that you typically this is done is using what is called smoothing spline. What you would do is that you use regularization to control the complexity. So instead of just doing these constraints and trying to find the number of knots that you're going to use, what you would do is that you then use this penalty term. So again, this is where the previous concepts that we talk about in terms of Lasso and rich regression comes in, right? So again, this is a very common concept when we use regularization in machine learning. We always take a penalty term that is either the square or the absolute value of something, right? So in this case, I want my curve to be smooth, right? So what I would do is that I would take the square of my second derivative, and I integrate them and I use that as my penalty term, right? And you then basically use this loss function to basically find the best values of your polynomials, and your that will actually give you the best fit to your data, right? And this is how your cubic spline actually works. Cubic spline is of course extensively used all over the place. I think this is by default. Whenever someone sees a x versus y plot and they see that there's not a linear relationship, they will just throw in a cubic spline and hope for the best. Okay, not necessarily a good strategy all the time, but it actually works more often than not. Okay, so it also has been used in material science, of course. So for example, there's a spline-based modified embedded atom fitting. So if you do not know what an embedded atom method is, it's basically a potential that predicts the energies of the atoms and forces on the atoms with respect to things like the atomic positions of the atoms, right? This is usually based on some pairwise term as well as some embedding function, right? It's too much of detail to go through with you on what these are, but very often they basically use cubic splines to basically approximate, for example, that relationship between the pairwise distance and your energies. They also use cubic splines to fit things like the embedding function and so on and so forth. Okay. All right. Just to show you how to do cubic spline fitting in SciPy. So this one you don't actually need your scikit-learn to do. Under SciPy, there's the interpolate package. There's something called cubic spline, and that's all there is to it. You basically call a cubic spline, you give it your x and y, and then they will find the best cubic spline. And then to perform, let's say you want to interpolate within the new space, you take that fitted cubic spline function and give it the new values of x to predict the values. Okay. But for the final part of our linear methods, we're going to talk about one very specific set of basis functions, which is Gaussian basis functions, right? Now, Gaussian basis functions have this form, okay? It's basically an exponent of x minus the mean of x squared times some prefactor, right? Okay, and what this means is basically they are Gaussian functions that are centered at x of m. Okay, so when x is equals to x of m, this is equals to 0, and you have your exponent of 0, right? Now, there are also other functions that are somewhat like the Gaussian basis functions, right? So this includes things like the Lorentzian, which have this function form 1 over 1 plus kx squared. The difference is in basically the shape of it. It still looks very Gaussian-like, but it is not exactly Gaussian-like, right? The way that the width of the decay of the function works is a bit different compared to your Gaussian basis function, right? And that you can, of course, also combine different types of basis functions of this type. For example, the Gaussian Lorentzian function. There's another type of functions called the Voitian functions, so on and so forth. Okay. Now, all these you do not really need to know the specific details, but you do need to know how these Gaussian basis functions are applied, right? And one of the most common ways in which you apply such basis functions is in fitting of data that seems to be made up of Gaussians, right? And one prime example where this is applied is basically Rietveld refinement, right? I heard one of you talk about NANO110. Okay, that is your crystallography course, right, XRD? Oh, molecular modeling, okay. Anyone have taken David Fanning's XRD course, characterization course? Yeah. So you learn about Rietveld refinement, right? So basically, Rietveld refinement is a form of machine learning where you essentially are trying to fit your measured spectra to some set of known spectra and trying to figure out what is inside your sample, right? And the way you do this is basically you look at all this neutron powder diffraction of this phase, which is calcium uranium oxide. And you essentially think of this as essentially one Gaussian over here, another Gaussian over here, another Gaussian over here. And what you want to do essentially is to treat this as essentially a summation of Gaussians. Okay. Now, of course, this is not the only situation where you actually would do this. For example, people frequently do this for XPS data as well. People do it for X-ray diffraction rather than neutron powder diffraction. Essentially, almost any kind of data that seems to be made up of a summation of Gaussian peaks, you can actually use such an approach. Okay. Now, the way that Rietveld refinement works is basically you define what is called a peak shape function. So the peak shape function is this multiple convolution of several different functions plus some background. Okay, so you have one function that corresponds to instrument broadening, another one corresponding to the wavelength dispersion, and another one correspond to the specimen function. And all you want to do is basically you plug this into this summation over here. And what you're going to do is that you're trying to minimize the square error between the observed intensities and your your linear combination of your peak shape functions. Okay. Now, basically, so this is just a linear least squares problem. Okay. So obviously, there's a weight involved over here. That basically just customizes which of those peaks whether it is at the low wavelengths or high wavelengths that you want to give a higher priority to. Okay, so this is just a modified form of your standard least squares regression. Now, the typical functions that are used is basically what is called a pseudo void function, which is a mix of a Gaussian and Lorentzian function. And what you then do is basically you use your standard least squares linear regression techniques, and you try to find your beta B1 and your LJs that will give you the best fit to the data. And from that, then you go ahead and determine what exactly is the crystal structure that you have in your sample. Okay, so this is one example where you can use such a technique. Now, other than Gaussian basis functions, you can also use more sophisticated functions like wavelets. The nice thing about wavelets is that they actually form a complete autonomous basis. What this simply means is that any function, okay, that functional relationship can actually be modeled by some summation of wavelets, okay? And I'm not going to write down the analytical form of the wavelets, but suffice to say, these are basically what they look like, okay? So these are all your wavelet functions, and essentially what you're trying to do is to determine which summation of all these wavelets together as well with the mean positions of the wavelets is going to give you the best fit to your data, okay? And again, it is a complete autonomous basis. You do need to truncate. You also need to shrink and select towards some sparse representation, okay? So you are not going to, you can't actually use an infinite basis, okay? So you actually do need to select your basis up to a certain value, either in terms of time or frequency or energies, okay? So the nice thing about wavelets is that unlike other types of basis function, it actually can represent both time and frequency localization very efficiently, okay? So, and this is actually a very desired feature for certain types of data, okay? Now, just to show you where it is used, so for example, in NMR spectroscopy, so people have actually applied wavelet fitting to your NMR spectra to basically try to suppress some of the background noise that you actually measure with your instruments. So for example, there's this large unwanted spectral line. And what you would do is that you actually use wavelet fitting to basically get the key data out of the spectra and then remove out that unwanted spectral line, okay? You can also use it for noise filtering, as well as if you sometimes want to detect whether your sample actually comprises of a mix of phases rather than just a single phase. You can also use wavelet fitting, okay? All right. Another area where this is actually used is in just another example is in X-ray absorption spectroscopy. So in the X-ray absorption spectroscopy, you very frequently you have this very long tail beyond the edge. So this is actually called the near edge, and this is called the extended edge. And basically, this extended fine structure actually contains a lot of information about your atomic chemical environment. What this means is that you frequently, by analyzing this extended edge, you can actually figure out whether there is whether this is an atom in a tetrahedral octahedral, or whether there are some distortions of that chemical environment. And the way that people do access analysis, and this is a very well-established field of application, is that you first subtract out your background noise, you convert this into K-space, which is your reciprocal space, using a Fourier transform of some sort. And then you then do fitting, and then you basically transform the K-space information back to real space to basically get information like what's your first shell bond length and that sort of thing, right? Okay. So now this kind of analysis, there are a lot of software that has already been written to do this for you. So it is not actually important for you to learn how to implement that yourself. This is really more for your background, that this is what is going on behind the scenes of the X-ray absorption spectroscopy software that you are using. Okay. All right.